Hi, in this video I will talk about stability of storage processes with general release rates. This is based on the recent joint work with Alex Mijatovic from Warwick and NIKOLA SANDRIČ from Zagreb. The storage process that we study has the following dynamics. It starts with a non-negative level x. Its positive increments are given by a non-decreasing pure jump Levy process or a subordinator, so a Levy process with non-negative jumps that can be both of finite or infinite activity. And the negative increments are given by this release rate R, that is state dependent, and positive if and only if U is greater than 0. And this means that when the level of the storage is 0, negative release rate will also be 0, and that will imply that X only takes values on the positive half line. Storage processes have a very rich history. The first results on existence and stationarity in a simple compound Poisson input case were given in late 70s, early 80s. Exponential ergodicity was investigated again in this simple case in the early 90s, and more general results for non-decreasing inputs that can be of infinite activity were given in early 2000s. And the modern advances are motivated by a lot of applications. For instance, storage models have been proved to be scaling limits of infinite server queues, and this led to a more detailed study, in particular in special cases, for instance, when X is a shot noise process, so release rate is proportional to the storage level. Explicit formulas were provided for both the stationary measure and return times, in both cases for finite activity. This is paper by Boxma and Mandias, and Boxma, Kela, and Mandias provide also explicit formulas in the infinite activity case. And there have been extensions to a fine release function with two-sided jumps, so when input jumps can be negative. The goal in our paper is to vastly extend the model by considering general release rates that can be constant, affine, but also sublinear, superlinear, and so on, and also study non-general inputs that can be finite or infinite activity and can be heavy or light-tailed. And we want to use modern probabilistic technique to establish tail bounds, so understand stationary law under these general assumptions, and also establish convergence rates to stationarity. So we will study both convergence rate to stationarity and the stationary law itself. Because we start with such a general goal, we first need to establish the conditions under which stability occurs. So we have a lot of conditions which will lead to a non-stable behavior. For instance, let me briefly explain. R will be the release rate, nu is the Levy measure, nu bar is its tail, and mu is the first moment of the Levy measure. And in the finite first moment of the Levy measure, if the release rate is smaller, asymptotically smaller than this first moment, we see transients, and if the release rate is bigger, we see positive recurrence. And if they're the same, we see null recurrence. And in the infinite moment case, if the input process is, for instance, alpha subordinator and release rate is u to the beta, is some polynomial, we see transience if alpha plus beta is less than 1, and positive recurrence and ergodicity if alpha plus beta is more than 1. Because we look at a very general model, we also see a very general range of phenomena. And of special interest is this positive recurrent case, where we want to classify all possible behaviors of the storage process. So to do this, we prove two main theorems, one that classifies upper bounds and the other one that classifies lower bounds, and together they provide a general picture. But to illustrate the main findings, we will first summarize the main results in the special case when the release rate is a polynomial of this form, u to the beta. So here note that we use this approximate here, which stipulates that we only make asymptotic assumptions on the release rate. The behavior of the release rate on compact sets will not significantly impact the behavior, the asymptotic behavior of the model. So this is the table that explains everything that we can see in this case. When we have a asymptotically constant release rate, if the input Levy measure has exponential tails, we also see exponential tails in the stationary measure and in ergodicity. And when the input has polynomial tails, we see polynomial tails in stationarity and in the convergence rate. And two interesting facts to note: the critical exponents are the same, which indicates that storage process explores the tails at a linear rate. And secondly, the stationary measure has one less moment than the input measure, which means that the marginals are asymptotically getting heavier and heavier. In the case of asymptotically linear rate, this case includes shot noise processes. We see exponential convergence for all input processes that have at least positive alpha polynomial moments for any positive alpha, and the tail of the input measure and the tail of stationary measure have the same tail decay. So the marginals have the same tail decay throughout the evolution of the process. Exponential ergodicity happens almost in every case, but here we have a rather esoteric case that demonstrates that even in the shot noise case, exponential ergodicity can fail. So if the tail of the input is logarithmic, so extremely heavy, we see only polynomial rate of convergence. And as you can imagine, if we have extremely heavy tailed inputs, we also have extremely heavy tails in the stationary measure. So maybe not very realistic, but certainly interesting to see. Even in this case, exponential ergodicity might fail. When release rate is between constant and linear, when it is this polynomial of sublinear type, the requirement for exponential ergodicity the exponential ergodicity no longer requires full exponential moments, but it does require all finite polynomial moments. So we have this stretched exponential condition that depends on the beta. And here the input measure is slightly lighter than the stationary measure. So the marginals are getting marginally heavier as time goes to infinity. The biggest impact of this beta parameter is on convergence rate. So you see when we go from constant to linear release rate, we go from slow polynomial to very fast exponential rate of convergence. And this can be illustrated well by this beta. So when beta is 0 and when beta is small, this is a slow polynomial rate. And when beta goes to 1, this goes to an arbitrarily fast polynomial rate, which means that there is a continuous transition in the convergence rate between linear and linear release rate and the constant release rate and linear rate. And the last case that we want to highlight here is the case where release rate is superlinear. In this case, we see uniform ergodicity for all input measures that have polynomial moments and any type of polynomial moments. And uniform ergodicity means that the convergence rate does not depend on the initial condition. And in some sense, that means that this superlinear, very fast release rate shrinks the state space, and in terms of the convergence rate, this process behaves similarly to Markov chain on finite state spaces. Last point I want to make here is that this is also the only case where the input measure is heavier than the stationary measure. So marginals are getting lighter and lighter as time goes to infinity, precisely because this super linear release rate is shrinking the process, pushing it towards the origin at such a fast rate. So this table describes various phenomena that we can observe when we study storage processes under these general assumptions. Now I'm ready to state the main theorems which capture these results, and of course a lot more than that. First one is dedicated to upper bounds, It requires X to be irreducible, aperiodic, and that all compact sets are petite, which is a standard assumption for ergodic Markov processes, and satisfied for storage processes under mild assumptions, which and these properties have been studied before because of the rich history of storage models. And to quantify the asymptotic behavior for stability, we need a Lyapunov function and a concave non-decreasing function that satisfy the following inequality, which is given asymptotically in release rate and as an integral over the tail of the Levy measure. And this condition suggests that only asymptotic properties of release rates will matter as the inequality holds for R of U plus V when U goes to infinity. So properties of release rate on compact sets should not impact the stability of these models. Directly from this inequality, then we obtain two bounds. The first one is on the tail of the stationary measure, upper bound on the tail of stationary measure, and second one is on the convergence rate, which is given via function phi. Lastly, maybe a technical detail, but if the Lyapunov function is constant, then this will give us a uniform ergodicity. So this is what happens in the superlinear levels of R. Okay, so this is one part of the story. These are upper bounds, and lower bounds are actually much easier to understand in these contexts. The requirements are the following one. The release rate has to be linear or needs slower growth, or slower or sublinear, which will imply that this RU divided by U log U, this limit is equal to 0. And then there's this interesting condition that 1 over the tail of the Levy measure is submultiplicative. So this essentially states that the tail decay of the Levy measure has to be exponential or heavier. So this condition will be satisfied for exponential decay of Levy measure, for polynomial decays, even for heavy logarithmic, but it will not be satisfied, for instance, when the Levy measure has a compact support. And this is the case where we cannot get lower bounds. So under these two assumptions, we can directly obtain lower bounds on the tail of the stationary measure, given in terms of U minus epsilon, U to the power of 1 minus epsilon for any epsilon greater than 0, RU, which is the release rate, and nu, which is nu bar, which is the tail of the Levy measure. And if we can further obtain a bound on the speed of the tail exploration for the storage process, this will lead us to this will yield a lower bound on the convergence rate to stationarity. So this is the main result on the lower bounds. And the remarkable thing about these results is that while they're, as you can see, the result on lower bounds feels quite simple, we can directly write it down in terms of the tail of nu and release rate. In heavy-tailed regimes, all the heavy-tailed regimes in table and much more, these lower bounds match the upper bounds and give sharp asymptotic rates of convergence and sharp asymptotic tail bounds on pi. So we can fully characterize the finite moments of pi and understand how fast we converge to stationarity, which is the main contribution of our work. Before we end, I just want to say a few words about the proofs, so how we prove these two main theorems. The upper bounds are proved via classical Lyapunov drift condition. So here we refer to Tugford-Gillin. And this is quite a simple procedure. From our inequality, we can directly obtain a Lyapunov drift condition. So we have this bound on the generator of Lyapunov function v, which asymptotically decays as phi composed with v. And this gives us pi integrability of the function phi composed with v, which provides via Markov inequality, an upper bound on the tail decay of the stationary measure. Moreover, the function phi governs the return time growth, and using the regeneration structure, we can obtain an upper bound on convergence rate in stationarity, which can be both exponential or polynomial depending on the function phi. For the lower bounds, we need to obtain two facts about the process, and we do it with a simple Lyapunov function, which can be chosen in most cases as a linear function on the complement of the origin. Here we want to estimate the generator with respect to the reciprocal of the Lyapunov function to obtain the function phi of 1 over u, and this will be a proxy for the duration of the excursion from a compact set. Secondly, we need to choose an interval from L to R and pick some x in this interval. And what we want to estimate is the probability that the storage process exits this interval on the right, and we want to understand how this probability decays for a fixed x as R tends to infinity. And for storage processes, it turns out that this probability is modeled by is well approximated asymptotically by one large jump of the input process A. So this gives asymptotically sharp bounds, and with these two functions then satisfy the recent L drift conditions, which use this information on duration and size of the excursion to provide lower bounds on the tail of the invariant measure and the convergence rate to stationarity. And those are the main ideas about the proofs, and that is how we can provide matching asymptotic bounds on the storage processes with general release rates. Those are the references that I have mentioned during the presentation. Thank you for your attention, and if you're interested in more information, you can look at the paper. Thank you.